Morning. My name is Itziar Alonso. I work at Techniker, and I want to welcome you all to this session focused on demand flexibility and energy efficiency. That is being organized by FATE and Techniker in the frame of the AmBIENCE project. Before we move to the presentations, Roberta will share with us some technical messages about how to go ahead with this session.
Thank you, Itziar, for giving me the floor. So yes, I will give you some technicalities. I would indeed ask you to make sure that your full name appears in the participant list, but also that your microphone is muted, especially when there are presentations going. If you have questions to the speakers or in general, please ask them through the chat, or you can raise your hand and we can unmute you so that you can ask your questions verbally. If you have any technical issues or questions, you can address them to me, Roberta D'Angelo, PPA, again via the chat. One other small note on the recordings. Today's presentation is being recorded, but only the presentation part will be disseminated, whereas the discussion part will be rather kept internally. So I would pass the word again to Itziar, and thank you for joining.
Thank you, Roberta. So here you have the agenda that we have defined for this workshop. First, Francisco Diaz, my colleague from Techniker, will talk about the market and regulatory framework, enablers and barriers. Then we will move to OptiCogen Platform project that will be presented by Ainhoa Galarza from FATE. Then Francisco will come back and will present the project NIERMBO. Then it will be after that, there will be time for AmBIENCE project, and we will focus on different topics, and I will make a presentation, and then I will give the floor from the different partners that have been involved in this project. And at the end, of course, we will have some time for making questions and having some debate or some discussions about the workshop that we have been talking about and different topics that may raise. So this is the agenda that we have defined. So now I will give the floor to my colleague Francisco Diaz that will talk about market and regulatory framework.
Thank you very much, Itziar, for your presentation. I am Francisco Javier Diaz. I am coordinator of the infrastructure sector in Techniker. And I'm going to make a short introduction to the theme of the workshop, that is the market and regulatory framework, enablers and barriers. The first one that I would like to show is to enhance is the energy performance contracting concept. What is the energy performance contract? It's a contractual arrangement between a beneficiary and the provider of energy efficient improvement measure, verified and monitored during the work of the contract, where investments, work, supply and service and the measure are paid for in relation to contractually agreed level of energy efficiency, improvement, or other agreed energy performance criteria, such as financial savings or the use of renewables, etc. Later we will come back to this concept, but something that I would like to announce is to the importance of the measurement and verification for the kind of properties. We have to monitor continuously the contract, the measures, the actions, the energy consumption, and the results, the outcomes, in order to immediately and indisputably measure and verify the achievement of the contractual targets. But other thing that I would like to announce is the situation of the ESCO market in Spain. ESCO, because is the central actor in this kind of contracts, and of course in this kind of management that we plan. The situation in Spain of the schematic in the smart is a medium, because you have a very good market size and is implementing in various building sectors, has longevity and market value, but perhaps the worst point is that the growth curve of the market is not good, but could be steady or mature. We don't know exactly. But about the flexibility services, the situation in Spain, the market is very bad. As you can see, the levels are very low in demand response, in the level of flexibility. We hope that these markets will be improved and will be close in the near future to other European countries in the environment. Why? Well, because there are several barriers identified. Of course, legal barriers are very known. Lack of regulation, the flexibility in Spain is trivial. Market barriers are also important. Limited access to various market options or demand options.
Francisco, sorry to interrupt, but we are seeing the same slide. So if you can please share your screen, otherwise I'll share mine, because we are still seeing the same intro slide.
I don't know what. Sorry, I was only comparting the one presentation. Do you see the
I think it's because it's there who's sharing the screen now.
Yeah.
So,
now it's correct. You are
That's
seeing the market values.
But I can do it so that
Move the presentation. Oh, we are in the same computer, so that's not the problem.
Okay, you are seeing market barriers.
I think we see slide number 4.
It's market barriers, Ainhoa.
Just the agenda.
Also no.
Now?
Yes.
Okay, thank you. Sorry for the inconvenience. About market barriers, we have limited access to market options. There is a high concentration with high entrance costs, absence of clear support schemes for renewables. This point has improved a bit lately, but only a bit. And very important, there is no the regulation about the role of the aggregation. Is an actor that is not regulated in Spain till now. The next barriers are technical barriers. Of course, these barriers are not so different from other European countries, and interoperability is a common barrier. Cybersecurity issues, people are worried for cyber attacks, hackers, etc. Liability issues, las cooperation procedures, and that access to distributed renewable production and generation, that is something very good for foster the market. And also local barriers, lack of knowledge. One of the objectives of this webinar is to spread some knowledge about that. Opacity of energy market and demand anesthesia. Consumers used to be reactive. This last point is also changing, because I would like to focus on three important milestones in the last times in Spain. First one was the Royal Decree in 2019 that allows direct consumption for local distributed renewables with some restrictions, like the distance between the generation and the consumption and the other things. But of course, it's a very high advance in comparison with the previous situation. Other milestone very important was last year, that the publishing of the new hourly tariffs in the electricity, and that will foster the demand side management. And finally, the Ukraine war, that, as you know, has the result of a very increase very much the prices of energy. These are the first one is the graphics of the price of gas. That's in the last year, and you see it here. It has increased continuously, and especially in last months, because of the war probably, but this is something not only by the war, I suppose. And the electricity price in the 20s, you can see it was steady, more or less, during several years, but in the last year has increased very sharply, especially machine price. This increase of energy prices is opportunity, because it has increased the margins of energy management. You have more room for the energy performance contracts, but by the other hand, there is a great uncertainty about how this will be evolved in the next months. Next year, nobody knows, because of course the war and the instability. Of course, this implies large financial risks that is not good for this kind of contract. Well, we can go deeper about these points in the final phase of the workshop in the questions you want. Thank you very much.
Thank you, Francis, for making this market and regulatory introduction to the topic. I think that now Ainhoa Galarza from CEIT will make a presentation about the OptiCogen project, that is Plataforma Inteligente de Datos para Plantas de Cogeneración. Ainhoa, the floor is yours.
Thank you. I will try to share my screen. Okay, I think you have to stop sharing yours.
Yes, I will stop sharing our screen.
Okay, so I think you can see the presentation now.
Yes.
Okay, so thank you. As Itziar said, well, I am Ainhoa Galarza from the Transport and Energy Division at CEIT, although the ICT division here also contributed to this project, which I'm going to present today, which is a smart data tool for cogeneration plants. Oh, wait. Okay. The project's use case is the Basurto University Hospital in Bilbao. It is compounded of 15 buildings inaugurated at the beginning of the 18th century. And the energy services of this hospital are provided by Veolia Group after this ESCO won a tender to renovate the thermal and electric installations to improve the user's comfort, to ensure climatization and electric supply, and to reduce energy costs. The ESCO then undertook an energy audit, renovated the heat and cold network and assets, and installed a cogeneration system. So the OptiCogen project, which I'm going to present, is related to the management of the energy acquisition and selling related to this cogeneration system. The project was financed by the Basque Business Development Agency through the HASITEC program, and the partners of the OptiCogen project are the ESCO, Giroa Veolia, as the water, waste and energy management responsible, Genelec Systems, which is specialized in systems automation and was in charge of the monitoring and control of the power generation facilities, and CEIC as a research center and in charge of the data analysis, the artificial intelligence and virtual analytics development. Okay, the main challenge for the management of the energy acquisition and selling was the increasing complexity of the cogeneration system. As you can see in the figure, with a large number of variables provided by instrumentation, sensors, monitoring systems, the SCADA of the system, different websites, etc. With at the same time a very heterogeneous kind of data. So it was concluded that the optimal operation and control of the cogeneration system could only be understood from a holistic point of view and taking into account all the data that affect the plant, and not only the data provided by the SCADA. And also, it was important that these data are often incomplete. Sometimes they are inconsistent with each other, or simply they are erroneous. So the proper processing of this data, the analysis and synthesis exceeded the ability of the plant personnel just to decide the actual system status. The components of the OptiCogen tool that was developed are mainly three. The first one are short-term predictions models based on artificial intelligence for predicting electricity price. Although the market price also was acquired from OMIE, which is the electricity market operator in Spain. And finally, the thermal power demanded for the buildings is also predicted. These predictions are done at zero hour and for the following 3 days, because the strategy was to decide the strategy for the weekend on Friday. So 3 days was needed for the time horizon for the predictions. And the second component of the tool is the recommendation tool, which recommends the working hours for each of the 2 cogeneration engines of the system. So in order to do so, this component uses a database with the predictions from previous component, around 10 different raw databases, such as, for example, the price for gas, the price for CO2, meteorological predictions or meteorological historical databases, plus the status of a hot water storing tank. So when the cogeneration engines are working, the energy is sold to the grid, and At the same time, the heated water can be used directly on heating system, hot water system, or just stored in the deposit. In addition to the recommendation for the engine's operation, the tool is also allows a what if else scenarios, which I will try to show in a minute through a demo. And finally, the last component of the tool is devoted to the graphical display of the results, as you can see in the graph. So this display is also interactive, and it includes some historical data for analysis that I will show you if I can. Wait a moment. If I can bring, yes. I think you are still seeing the slides. Is that true?
No, we can see the
website.
The website, yes.
Okay, perfect. So this is a demo website prepared for different projects. We can go to our use case. Yeah. So in this slide, we can see the predictions here for the electricity price. And we can also see the prediction for the thermal demand of the buildings. We can also decide to use the forecaster, or in this case, we could also acquire the data from AmBIENCE, but in this case, this is only possible after noon, and it wouldn't be possible to use this, for example, for the weekends. So we can't use this. We can use our forecaster results, or we can also use other forecasting algorithms from a specialized company. So we could use each of the three. Let's maintain ours. So above this, we have the recommendation for the operation for each of the two motors, of the two engines, sorry, for the cogeneration system. We also have an estimation for the benefit we are going to obtain selling the energy to the grid, and other different results, which are shown graphically. And as I said before, this is interactive. So we can, for example, analyze what if else scenarios. So what will happen if we move the estimation for the energy price? So at some point, the recommendation given in the above part would change. So for example, if I move the prices, you can see that the recommendation is changing. And the same goes for the thermal demand of the buildings. Apart from this, the plant operator can decide to change the recommendation. So for example, can switch on or switch off the engines, and for whatever reason, right? We can see the effect on the benefit. Well, in this case, it's bigger because I have changed the prices, but he could see, or they could see, if the benefit is going very low, for example. So apart from this, as I said, we can also see historical data, for example, for past days. In this case, we have real prices and real demand, and we can consult the benefit obtained in different past days. Or we can also go to a month summary. We can see here real prices, real demand for each of the days of past day, of current day, for example, and seeing this information and the percentage of the time that the engines have been working, the cogeneration system has been working, for example, the operator can decide to increase working hour if the minimum share is not achieved. So just to turn on the system for longer times. And finally, we also have the summary for this year, and we can also go to the configuration part where we can establish the parameters for the cogeneration engines, or for example the size and temperatures for the deposit. So we can, as I said, we can do all these things with the tool, and I will go back to the presentation.
No presentas tú.
So are you seeing now the slides?
Yes.
Yeah. Okay, perfect. So let's see if I can move on. Yeah. So the results of the project, if we focus on the technical achievements, are that all the databases are preprocessed. They are centralized in one database, which is formed by very heterogeneous sources. The innovative models were developed, and sometimes ensemble of models to predict electricity prices and heat power consumption. And the decision process for the cogeneration system was improved. It is possible to do this kind of exploratory sensitivity analysis, and the results are easy to understand. And for the project as a whole, it is estimated that the use of this tool decreases in a 5% both the consumption, the gas consumption, and the CO2 emissions. And in general, it's also enhanced the reliability regarding thermal and electric supplies, and the user comfort and satisfaction are improved. So this is all from my side. I give back the floor to Francisco. Thank you.
Thank you, Ainhoa. Now Francisco will talk about NIERMBO project. So if you...
Hello, everybody. I'm Francisco Javier, and I'm going to present the project NIERMBO. NIERMBO is the acronym for Near Zero Energy Building, integrating renewable energy, being installation, maintenance, and operation. It's a project funded by the Basque government under the Strategic Architect Program. It started in March 2019 and finished 1 month ago. It has a total budget up to 3 million euros. The objective of NIERMBO is the transformation of the residential, industrial, and commercial buildings into nearly zero energy buildings. For that, the idea is to use the energy more efficiently and sustainable, to improve the operation and maintenance, but being more smarter. And the idea how to achieve this is the development of software for application for monitoring, for optimization, or service consumption, especially taking advantage of demand response, especially of local consumption. The other way to achieve these objectives is the use of big information modeling. from the design phase to the operational phase, and to build a platform around this context. In fact, is to develop the 6th and 7th bit levels to providing digital tools integrated with the geometry or the building, and use this model as the core of the platform. The final result will be improve the operation and maintenance of the building to be nearly zero energy. The participant roles in the project was Giro Veolia, important ESCO in the Basque Country. You can see also in the OptiCogen projects. Other company very important in Basque Country in engineering is SENER. System Plan, that is a CCMS vendor, has a very used system named Prisma. ACR, a construction company. Batteries manufacturer, Cegasa. Nomusa, because there is a air condition boiler heat pump manufacturer. Sigor, manufacturer of inverters and power electronics, and 3 technological centers that will address different technologies. Technical will be the developer of the wind technologies. Ikerlan was the developer of the energy efficiency technologies, and Tecnalia was the developer of the virtual reality and augmented reality technologies. Following this schema, the result of the project, and well, about the wind-based digital twin. We apply this concept in the design phase for the design of the building, in order being able to make simulation of the thermal behavior of the buildings. Follow the life cycle of the building. This model is also used in real-time monitoring and others, as you can see in the image, showing what is the asset that needs any maintenance or any action or any alarm. For that, it's very important to integrate the model with all the systems that manage the building, like the SCADA, the building management system, the maintenance system, NIERMBO, or any IoT devices. At the end, the use of the BIM model during all the life cycle of the project of the building, sorry, allows to discover the gap between the theoretical performance that was done in the design, in the simulation, with the real performance that will be the assurement in the operational and maintenance phase. About the building management system, we developed a building remote supervision and management systems. The system monitor the different equipment and devices in the buildings. is a cloud-based database, and with the data we make and the price prediction, as you can see in the previous project of OptiCogen. We make consumption and generation forecasting. With this forecasting, we make a strategy for optimize the management of the energy and generate the corresponding high-level commands and to the systems, to the equipment. And finally, about the immersive technologies for the maintenance and operation, we developed 3 modules. One module that makes the conversion from the BIM model, the IFC file, to a more visualization friendly or web friendly format that it could be used for visualization in a web browser or in devices with constrained capability. This module will was used in the virtual reality web module that visualize the BIM model of the building embedded in the Prisma maintenance software. Prisma maintenance software is the software developed by the Platinum and so. And finally, the augmented reality module that is be able to show additional information of 3D objects in mobile application or in this kind of devices. Well, this is all on my side. Thank you very much.
Thank you, Francisco.
I give the floor to.
So now it's time to talk about the AmBIENCE project. So as I have said at the initial part of this workshop, I will give you a brief presentation of this project, and then our project partners will provide us with further detail on the concept and the developments that we have achieved. First, I would like to explain that AmBIENCE is an European Union funded project which stands for Active Managed Buildings with Energy Performance Contracting. It extends the concept and approach of business as usual energy performance contracting to active buildings. We understand as active buildings whose assets can be controlled in an active way to enable the use of flexibility. So this active managed building with energy performance contracting makes it available and attractive to a wider range of buildings. This is made possible because the advances in different technology fields that makes AmBIENCE go beyond the passive building concept by adopting the active control approach, using buildings' inherent flexibility to further reduce losses or costs, maximize the use of self-generated renewable energy, and offer services to the grid and also to the market stakeholders. The vision of AmBIENCE is the reduction of building emissions in the European Union, as well as a lower energy consumption, thanks to the application of electrification combined with active control. And our mission is to improve the economic attractiveness of building emission reduction measures by combining energy efficiency improvements with electrification and active control. What has been done? Because I will later explain that we are almost finishing the project that started in 2019. We have extended the energy performance contracted concept to include demand response value streams, valorizing the flexibility that is available in active buildings. We have made this active building EPC concept applicable, available to a broader range of buildings, including residential and including the cluster of buildings. We have developed a tool that supports the forecast of demand response value stream in the EPC contracting phase. We have built the concept, the tool, and measures and verification methodology with 2 real buildings. Afterwards, we will provide you some insights about the pilot in Belgium. And we have also engaged with all relevant actors and stakeholder groups to remove barriers and to ensure or at least improve applicability. Why we have done it? Because we want to reduce emissions by actively steering electricity consumption to times when the carbon intensity is low. Also to reduce energy costs by actively steering electricity consumptions to times when the prices are low. Also to accelerate electrification, thereby by further reducing emissions by leveraging the value of active control of flexibility, lower prices and flexibility services. And of course, to support investments in more wind and photovoltaic by increasing demand for emission-free energy and by offering flexibility services to deal with the generation variability and congestions. Who will be benefits of AmBIENCE? Of course, the environment and the society, since greenhouse gas emissions will be reduced. Consumers, of course, because energy cost savings will be achieved by shifting consumption times to times when the cost is low or by offering flex services. Energy system stakeholders, since they will have access to more undistributed flexibility. And at the end, of course, ESCOs, since they will see how the EPC contracts are enriched with higher value and applicable to a wider selection of buildings. This will grow the ESCO's business opportunity. So as I have said, AmBIENCE is a European project. 8 partners are involved in the development of this activity, coming from the research and also some commercial partners, coming as from 4 different countries. From Belgium, we have Vito, that is the coordinator of this project, but of course we have Energy Invest and BPIE. From Italy, we have Enea. From Portugal, we have Inestec and EDP, Smart Energy Lab. And from Spain, somehow the coordinators of this workshop, that is Fate and Techniker. As I have said, this project started in June 2019, many years ago, because it was before COVID, and I think that it was a long time ago, and we'll finish this next month in May. So once I have provided you with this somehow an introduction to this project, now our colleagues coming from, for instance, from Inestec, João Paulo Fontoura will explain in more detail what we mean with active energy performance contracting. Then Sarnavi Mahers from Vito will explain the ABPM tool. The market potential and the experience of the Belgian pilot will be presented by Lieve Mastralen coming from Energy Invest. And at the end, I will give you some slides about the next steps that we are going to go through before we finish the project. So now I would like to give the floor to our colleague João, that who will be explaining the active energy performance contracting in more detail. So João, the floor is yours.
Thank you, Cesar. I just showing the screen. Can you see?
Yes, perfect.
Okay. My name is João Fontoura from Inestec. I'm here today to introduce the main concepts developed in the AmBIENCE project. First, let's introduce what is the energy performance contract, the main concepts. An energy performance contract is a mechanism that organizes the energy efficiency financing, which provides customers with a comprehensive set of energy efficiencies, renewable energy, and distributed generation measures. This contracting is often accompanied by guarantees that the saving produced by a project will be sufficient to finance the full cost of that project. A typical EPC project is delivered by an ESCO, who can relieve the client by proposing an option set of measures, giving performance guarantees for the project, savings, and payback time. And what's the difference between the classical approach and the one developed? Here we have the classical EPC, and now we have the active EPC concept. That is basically made in two ways: energy efficiency and demand response. For energy efficiency, save energy in long terms or permanent perspective. For example, lighting retrofits, building automation upgrades, or HVAC improvements, and building envelopes insulation. For the demand response side, we have the short-term reduction in energy demand. Might include turn off the dimmer, for example, lighting, or reducing the HVAC levels. The concept extended to the traditional EPC in three main dimensions. First is extending energy performance guarantees related to the energy efficiencies to include the valorization of the flexibility through demand response. Second, third, the EPC to a broad scope of buildings types like residential, hospital, education, offices, commerce, and others. Extending the scopes of the EPC to groups cluster of buildings under the concepts of energy communities. Here we have some examples of demand-side flexibility that is available. For example, it is very important to have this. Heat pumps, for example, lighting controls, energy recovery ventilation, electric vehicle, electric batteries, all this could help with the EPC contracts. And here, the main factors that affect the demand side. Demand flexibility is the most important. And we have the factors that design of flexibility as a product. It's very important. Available of technology, measurement and validation, privacy and security, customer perspective, and market access. All these will have the demand side flexibility. And now we have a value chain for this. We have the classical value chain for the business model that we can see that existing energy service value chain from the primary to useful energy. For primary energy, it's the energy that could be saved, like crude oil, natural gas, coal, etc. For the secondary energy, we have the type of energy that consider utilities, like cover electricity, distributed heating oil, natural gas, biomass, for example, and useful energy at energy supply contracting, that an efficient supply of final energy that is contracted, such as heat, steam compressed, and this measures at megawatt hours. And for energy savings, for energy performance contracting, we have the focus on reducing final energy consumption through the energy efficiency measures. The business model is based on saving guarantees, which is stated in megawatt hours. And the last one that is shown right now, the energy savings. For the energy performance contract, the focus is reducing final energy. No, sorry. Right now is okay. By adding this right now, the demand response and flexibility to the business models, the value chain can be extended. This is the green box that we have. The important measure is amount flexibility or flex watt hours. In this slide, you can see some specifics that roles that each these actors need to play. Here, it's important the EPC main actors and stakeholders are more similar to the classical EPC, with exception of the aggregator that accrues the flexibility from customers. And moreover, the necessity of flexibility and the possibility of pursuing demand response programs would make the prosumer the potential end user for the EPC project, and consequently an actor in active energy service. Here, this important thing that the demand response. This slide provides a summary of these demand response servers that are typical offer in AmBIENCE. Load shedding, as you can see, is one that requires few investment, in which the main benefits are from cost reduction by avoiding higher energy prices. Then load shifted can get extra benefits to the customers, and then load shapings require a higher smartness level of demand side. Here I just go quickly for the business models just to present. We have 13 business model options for based on demand and response, could be implicit or explicit. But the building types, we have the commercial building, public buildings, and residential buildings. And for residential buildings and social housing, all with implicit and explicit demand response. Here, just to check, just a generic model with the electricity supply, the facilitator, the acquired, ESCO, subcontracting, financial, all the relationship between them. And a generic ecosystem that show all the actors in the ecosystem. Now, the important part, the implementation of the APC. The general procedure for the APC project is divided into three main phases: pre-contracting phase, contracting phase, and performance phase. Here in this figure, you have all these phases together and all the sub-phase. Just quickly explain. I will explain each phase in more detail right now. The first phase is the pre-contracting phase. The first stage for identifying the potential that is divided in two phases: the pre-feasibility and feasibility study. The pre-contracting phase is the first stage for identifying the potential project and ensuring that it's a robust base to start a project. First, the pre-feasibility studies involves the collection and data analysis related to energy use and estimate consumption factors based on energy bills for the previous years. The feasibility study aims to uncover the strengths and weaknesses of the business and the resources required. The results determine whether the solution should be implemented. This phase is also determining if they should consider an APC or better to switch to a classical APC. The contracting phase. This phase is concerned to develop and implementation of the project. This phase is particularly important for the success of the project. And then, main measures and features the contractor are calculated in this phase. This phase is divided in two sub-phases: that's contract design and deployment. The contract design is where the main calculation and quantification on the terms of the contract and shaping the features for the active building EPC are performed. And the development phase is where the selected project design options are being installed and performed. The last phase we have is the performance phase. That phase starts after the installation of the equipment and signing of the contract. This phase refers to the period that the operational activity under the scope of the contract starts until the end of the project. It's divided in two phases: the operation and monitoring activities and measurement and verification procedures. The operation and monitoring activities are crucial for meeting the requirement of optimization of the equipment operation. It's necessary to check that the information sent to the new sensors and the smart meters are well recorded and does not cause any delays in the operation and demand response activities. Finally, in the many performance-based energy contracts are regular measurement and verification procedures done during the project to determine these savings. This procedures performance along with general operation maintenance activities until the end of the contract. Now the APC project is concluded. For me, it's finished. Thank you.
Thank you, Joao, for explaining us what we mean in the AmBIENCE project for active energy performance contracting. And now I think it's the time for Sarnavi Maes to explain us in more detail the AmBIENCE tool.
Can you see my screen?
Yes. Yes, perfect. Thanks. Go ahead.
Presentation mode. So I will discuss about the AmBIENCE tool. Let's say more high-level idea, and not trying to bore all of you with too much technical details. And I will also give a brief idea about the configuration subtool of AmBIENCE and the energy cost cash flow estimation subtool, which computes the operational cost savings and some other KPIs. So to start with AmBIENCE, so AmBIENCE has two major goals. And one of them is to calculate the operational cost savings and some KPIs, and obviously to check the financial viability of the renovations that will finally lead to the operational cost savings. Another third goal is to check for the performance guarantees when it's in operational phase. AmBIENCE is actually a large software tool, and has 5 different subtools. The configuration subtool configures different models of buildings, different equipments that you have in the building, let's say heat pumps or HVAC systems, PV, and other things. The gray box model creation subtool creates building models from measured data and weather information. The scenario creation subtool creates different scenarios of different weather scenarios and what would be the temperature and sunshine and those kind of things. All of these 3 tools, subtools, let's say, generates information that is fed into the cost cash flow estimation tool, which finally computes the operational cost savings, which is further fed into the economic calculation subtool, which checks for the financial viability in the end. So to go step by step, the first step of AmBIENCE is to create a baseline and reference configuration using the configuration subtool. The second is to create models of building using historical weather data and measured temperature, indoor temperature, sunshine, and other things. So once these 2 are done, we have again some information from the configuration subtool, which is fed into the financial calculation tool, which computes the investment cost, let's say, for the renovation. So the baseline configuration is typically a configuration that is pre-renovation, and the reference configuration is post-renovation. So there's some initial investment cost involved, which is computed by the financial subtool. Next, the baseline operational cost is computed. So typically, so based on the baseline configuration that comes from the subtool, from the configuration subtool, a building model from the gray box model tool, and a selected scenario from this tool that is fed here in the energy cost cash flow estimation subtool, it computes a baseline operational cost, which is then fed forward to the economic calculation subtool. And some baseline KPI reports are created based on the cash flow estimation tool, and it basically results in some energy consumption numbers, operational cost savings, CO2 emissions, and such. And exactly the same thing happens for the reference scenario or reference model. Once these steps are done, the economic calculation subtool generates an investment report based on the initial investment cost, the baseline operational cost, and reference operational cost. So these are mostly the covers the major 2 goals of AmBIENCE platform. The final goal was to check for the guarantees, which is done by the guarantee assessment tool, and instead of instead of using the historical data, it works on the operational weather data and generates a report to correct the KPIs and savings. So that was in short the high-level idea of the AmBIENCE tool. I will now briefly discuss the configuration subtool and how everything is configured, which is then fed into the cost cash flow estimation tool to compute the savings and consumptions. So we can introduce multiple commodity collectors. So let's say you have like a hot water collector, you have an electricity collector. You can put some cold water collector if some countries or regions need cooling as well as heating, such as Portugal. You can introduce a gas collector if devices in the building use gas as the energy source. Then you have some commodity consuming devices such as space heating, hot water, and some uncontrollable load such as refrigerator, TV, washing machine, some lights. I will explain later why it's called uncontrollable, or why do we consider it as uncontrollable in the context of AmBIENCE platform. Moving ahead, you can also introduce some commodity producing devices such as PV panels, which connect directly on the electricity collector, and commodity converting devices such as a heat pump. You can also put air conditioning units, chillers, but obviously they would connect to a cold water collector. And you can introduce some commodity storage devices such as battery, a battery. It could also be an EV charging, an EV vehicle that charges from the collector. And obviously these collectors, the green vertical lines, these collectors exchange with the outside, meaning they connect to the electricity grid directly. So the hot water collector could also be connected to the district heating network to exchange directly from the grid outside. But just for simplicity's sake, it's not in the picture. These are obviously the collectors are obviously cost coupled to commodity flows. So let's say PV generates enough electricity to push it back into the grid. The costs are considered, and the costs are considered on both ways, going out and coming in. So that's how the configuration is done for any simulation, for any operational cost saving simulation. And in a summarized way, it looks something like this. The simulation model, the configuration tool passes on a model something like that to the simulation model, where the inputs are segregated into non-controllable and controllable inputs, and there are some outputs which we can control, and obviously along with that the costs and consumptions are optimized. So that's about it for the configuration subtool. I will now go to the cost cash flow estimation subtool and I will end it with an example on the Belgian pilot case study on the amount of savings estimated by the tool for the Belgian pilot case study. So the goal of the energy cost cash flow estimation tool is to optimize the operational costs of a building. And the tool determines the flexibility in electrical consumption of different devices such as the heat pump, electric vehicle, battery, and computes operational costs. We also call this smart control. The tool obviously respects the occupants' comfort conditions by maintaining comfortable indoor temperature throughout the day. Some of the devices are considered uncontrollable, as I was saying before, and that's because of the tool doesn't consider them useful for flexible consumption, such as a TV, a refrigerator, because it's not useful to control them per se towards flexible consumption, even though when electricity is generated from the PV panels during the daytime, some of it is used directly for these devices, but it's not used for any smart control. Those devices are not considered under the umbrella of smart control. So I will dive directly into an example. So this example is without any smart controls. And we consider a 24-hour period for a residential building. And it has obviously the space heating using a heat pump, has some uncontrollable load and PV panels, and an electric vehicle for that charges to through the electricity collector. So this is a 24-hour period, and it starts at midnight and ends at midnight. So it's yeah, that's the duration. It's a 24-hour period. So as you can see in the graph for the PV panels, it generates somewhere around 30 kilowatt hours of electricity throughout the day, and the uncontrollable load devices consume some electricity throughout the 24 hours, but there's increased consumption during the day and in the evening. The space heating is active throughout the night. So this part, so it's after midnight, obviously, and in the evening, and except in the daytime for obvious reasons. The electric vehicle starts charging in the evening as soon as it arrives at the residential building, and charges throughout the night. Now this graph basically shows the consumptions, the different consumptions. As you can see, the off-take electricity that is drawn from the grid is shown in red. It's it's at 75% of the entire day's consumption. The injection electricity in blue is the amount of electricity generated by the PV panels and injected in the grid for some extra money, as in earned by the building owner. And finally, the self-consumption shown in green is the amount of electricity generated by the PV panels and consumed by the building. It's at 33% of the total PV production. The self-consumption is obviously free, generated by the PV panels, and did not cost grid offtake electricity prices. So the self-consumption actually plays an important role in our cost cash flow estimation tool, because it exploits the flexibilities based on this self-consumption. So I will then go over to the smart control example, where we introduce smart EV charging and smart space heating. As I was mentioning before, the uncontrollable loads are not under the umbrella of flexible devices or smart control. So it's exactly the same. The consumption is exactly the same as in the previous simple control example. But as you will notice, most of the space heating and electric vehicle charging has now moved to the daytime. So with the space heating, there's still some consumption in the night, obviously, but instead of using it in the evening, the space heating consumes PV generated electricity in the daytime to not immediately start when it's evening and it has got a bit colder. The electric vehicle, along the same lines, it charges using the solar energy the next day instead of charging in the night. And the tool already has a priori information based on a commuter profile. We create a EV charging profile based on commuter data, and the platform or the tool already knows that if the vehicle is going to be in the house the next day, it will not charge immediately in the night. So that's why it charges in the morning with the solar energy. And then in the consumption graph, this one, as you can notice, the offtake electricity has reduced from 75% to 24%, and the self-consumption is at 100% now. So the house with all its equipments is consuming all of the electricity generated by the PV panels. So this was the high-level idea of what it does. This is a more concrete example of the Belgian pilot study. It's done to compare obviously the simple control and the smart control case, and to put a number on the amount of savings possible with the smart controls or flexibilities that I was describing in the last two slides. So it's exactly the same example. The heat pump has a COP of 2.97. The PV panels are of I think 25 meter square area on the roof. The EV vehicle, we know from the commuter profile that the EV vehicle runs for around 30,000 kilometers per year, and it's the assumption made there is that it's always charged at home, at public charging stations, always at home, and the charging pole available at home is of 10 kilowatt, and the vehicle has a battery of 72 kilowatt hours. So for the specific case of simple control, the thermostat settings are kept to a temperature above 20.5 degrees between 7 a.m. and 11 p.m. and above 15 degrees between 11 p.m. and 7 a.m. And the electric vehicle charging is simulated as charges immediately after arriving. The results generated by the tool shows a consumption of around 15,000 kilowatt hours from the grid electricity, and self-consumption of around 2,600 kilowatt hours. The total cost ends up being 3,100 euros. And once we introduce smart charging and smart heating, we also introduce an additional constraint on the temperature, on the indoor temperature. So since we introduce smart heating, it might heat up the house when it's not required so much. So we put a upper limit of 21.5 degrees so that it doesn't heat up the house above that. The EV charging obviously starts next day. So with those assumptions introduced in the simulation, we see around 14,000 kilowatt hours of consumption from the from the grid, and a self-consumption of around 3,800 kilowatt hours. And our total cost for the year for the residential building goes to 2,647 euros, which is a savings of around 14.5% per year. I guess, that's all from my side. I guess questions will be at the end, if I'm not wrong. Yes,
you are right, Sanavi. Thank you for making us more clear what does it mean, the AmBIENCE tool for the AmBIENCE project. So I think that now it's time for the market potential and the insights about the Belgium pilot. So
yes, thank you, Ternava, and thank you, Itziar. What I suggest maybe is to start with the Belgian pilot and then do the market potential afterwards, because it's a good follow-up on what Ternava just presented. So let me just quickly share my screen. Can you see it in full presentation mode?
Yes.
Good. So quickly, what I wanted to share with you today is some key elements of the Belgian pilot. What's it about? What is the building about? Some insight into the flexibility potential, the methodology that we followed throughout the pilot, some key outputs, and then results building on the dynamic simulation that Sernavi just presented, and some conclusions. So the house itself is quite an old house, residential, built in 1912, what we call in French maison de maître, of quite a big house in terms of office space, 337 square meters. That's excluding the basement, which is about 60 square meters and a double garage at the back, but they are of course not heated. Occupied by a couple and 2 dogs, with a ground floor and then 2 floors on top of that, including a main bedroom and bathroom. 3 previous bedrooms were transformed into an artist space, mainly for workshops and courses. There's also an annex of the house that has been transformed into, or will be transformed into a main bedroom, shower room, dressing, and an additional artistic workspace. And then part of the house is dedicated to home offices, a living and dining room, small sitting room, kitchen, and an attic. In terms of heating, originally there was a fuel fired boiler, but that was very old, was almost, I think, 35 years old. When the house was bought by the new owners, a wood pellet stove was installed to heat part of the ground floor, and then a condensing gas boiler in 2016. Most of the lighting has been transformed since then also into LED lighting. Most of the glazing and the windows are first generation double glazing, so there is still improvements to be made there, except the home office space where the windows were replaced by high insulation glazing, meaning the glass only, not the, let's say, the old wooden frames, because of aesthetic reasons. There were some insulation works done. First of all, a terrace on top of the home office, you see it in a minute, and then also the roof of the bedroom, bathroom, basically because of water infiltration, it had to be redone, and so at the same time there was replacements done of placement of insulation. What's also very important is that the house, also of course because of its size, is being used very modularly. That it means that several spaces are not heated or only limitedly heated during the winter, or only heated, for example, the artist spaces when they are being used. Yeah. So it's not as if the whole volume is being heated all of the time during the whole winter, of course, which doesn't necessarily make it easy. So these are some pictures situated about 50 kilometers south of Brussels. On the middle side here, you see the front, the facade in red bricks. On the right side, you see the new gas boiler. On the left side, you see the wood pellet stove. And then you see on the bottom side the volume, which is quite complex, with the, let's say, the main volume being the old part of the house, and then on the side and below here also part of the original house, and also the part on the back, which you see here on the right top side, are original. But for example, the gray part on the bottom, that's something that has been added in the 1970s. As an extension. The same for the garage, which does not show on this picture, but which is behind the little block here on the top right side. Behind that basically is the double garage. Okay, and this gives you some ground floors. You see the what is that here? Salon, disinfect, home office, with on top of it the terrace, which you see here on the right side. And of course the existing volume here on the front side of the house, with the top floors. This is where the artist space is now, which is, these are these 3 chambres, these 3 rooms which are being transformed or have been transformed. And this shows you, for example, the ceiling of the home office space, which, as I said, is isolated from the outside on the terrace, but is not yet insulated from the inside, for example. Okay, some flexibility potential. Well, first of all, given the purpose of the project, electrification with the heat pump to replace the gas boiler eventually is, of course, a primary source of flexibility. The PV panels, which you will see in a minute, that are foreseen on the main and secondary roofs and some exterior walls. So there's eventually quite some potential. And then the electrical vehicle, which is already planned also. It will not have vehicle to grid capability, but it will have probably vehicle to load capability. So what we did is, of course, define and collected information and data on the building, on comfort levels and on energy consumption. There was an energy scan and an audit done as part of a local energy accompanying program proposed by the municipality. But the problem is that the energy scan is very high level, and that the audit, although interesting because it allows to get subsidies, it only uses theoretical heating data, theoretical temperatures, which is not really relevant, as I explained, because the building is used in such a modular way. So this is also why we had to go, of course, and wanted to go also to the static simulation and then the dynamic simulation using the AmBIENCE tool. So without going into details, so we did the static simulation, defining building model, and then determining, for example, the insulation levels, determining the needed power for the heat pump and also for the PV panels. And then we used the dynamic simulation first based also on a measurement campaign to really assess the real temperatures being used over a number of weeks, and also heat production on the boiler, on the existing gas boiler, because there was of course there's no energy management system or a building management system for the moment. What is also allowed is to assess the global heat usage of the building. And then the savings were calculated using the AmBIENCE tool, as Sanavi explained. Then there was some work done on implementing a monitoring solution. And then, of course, in parallel, the AEPC contract development and designing and implementing at least part of the monitoring solution and some lessons learned. So these are all the steps we went through. This is an extract from the energy scan, as I said, with limited interest. This gives you an overview. Again, I will not go into detail, but how, let's say, for every roof, for every wall, for every window, we determined, of course, the surfaces and then the U values before and after works, and same for the floor insulation. And then on the bottom right side, static simulation of the base case and the scenario with the insulation installed. And so you see that in that static simulation, there was already around 60% potential of heat savings. Okay. We then, of course, also for the business case had to estimate all of the investment costs, again, for installation of roofs and molds. And on the right side, you see, so that in itself was a total investment cost of about 85,000 euros. But then there are the PV panels, roughly 21,000, and the heat pump, another 10,000. So it's a total investment of around 116,000 euros. So quite a significant investment. And of course, question how to recover that investment. This is an example of in the basement where the boiler is installed. The measurement campaign was done here to collect heat data and heat consumption data. And then match that to the temperature measurements that were made. So quickly some outputs that generated. First of all, it allowed us to validate the AEPC business model for the residential case. And it also allowed us to define some requirements for active control and ABAPM integration in the home control EMS. Basically, this, of course, would be a much more simplified solution than you would find in a tertiary or public building. So we worked on the residential AEPC contract, also validated by some ESCOs. We worked on designing a monitoring solution that could be replicable for such a case. And we worked on a measurement and verification methodology for the residential case, again, quite simplified. Probably not based on percentage savings, but based on reaching an absolute energy level. And then there's the business case calculations that were done, which I'll show in a minute, and some other elements like the digital meter installed and the smart energy management solution, and of course the electrical vehicle that is being ordered. Quickly some results. So these are really the results from the tool as Sanavi explained to you, and with the different cases, starting from the reference case at the existing house as it was, and then the renovated building, including the insulation, and then the heat pump, case number 4, adding the PV panels, adding the EV charging, and then the 3 smart control simulations, smart heating, smart charging, and then the combination of smart heating and charging. And here you see basically how the total cost, of course, from 3,700 euros goes down let's say in the best case, the full case, case number 8, to 2,647. But if you look at the effective costs, it goes down to 1,100. Why? Because once you introduce the EV vehicle and the EV charging, of course, part of that electricity that is being charged, in this case specifically, can be charged back to the employer because the car is a company car. Yeah? And that with the difference between the cost for producing the electricity and the cost that is being sold, there is an additional cost saving. And then you see, of course, from case 3 onwards, that the gas, of course, disappears on the right side, gas consumption, which for 36,000 through the renovation goes to 15,000, but then as the heat pump is installed and the electrification, gas is being abandoned, and then electricity is being added. With the, of course, then in scenario 4, case 4, the PV production starting to kick in and allowing to also to progressively with the smart control to reduce the electricity injection. What's interesting to see is that in fact the potential from smart charging is in fact more important than from smart heating. These are some numbers, again, I will not go into detail of the business case, and that's so calculating on the lifetime of the installation and of the building. And there again, you see the yearly savings. So there's not a lot of difference in terms of investment, but there is quite a lot of difference in real cost savings. And you see on the last line, which increases from case 6 smart heating to 100 euros, but then with smart charging and smart heating combined with smart charging increases quite a lot. And they are very interesting measures, of course, as shown in the case. It's all, of course, still in this case a simulation. A lot of it is simulated, but it gives a good indication of the potential. So conclusions: renovation installation tailored for the heat pumps allows for about 60% energy consumption and cost reduction. If you then electrify with the heat pump from gas to renewable electricity, that allows for reduction of CO2 emissions. Adding PV further reduces the cost savings by another 20%, and of course increases locally produced 100% renewable electricity with quite a significant auto consumption. EV charging allows to monetize the investment and stimulate green mobility, and then the smart heating itself adds another 3% cost savings. The smart EV controls another 8%. So you'll see almost 3 times as much from the cost savings from the EV control and the heating again, as I explained. Okay, we can keep maybe some topics for discussions later on. So what I'll do now is switch to the second presentation, which is the one on the market outlook and potential. Again, of course, not much time to go into much detail, but quickly try to understand the driving forces behind active building EPC from different organizations' perspective. What is driving market potential, and then give some insight into generic market data also from the ESCO market in general. I have some stuff to show on the stakeholder survey, but there's not much time, so but you will have the info in the presentation handouts later on. Okay, so what could be the driving force for market actors to develop active building EPC, and why would they go and start using this in the first place? well, ESCOs, for them, it could be a way to improve the business case for EPC and for the classical, the existing APC in buildings. As we've seen, smart control does allow to some extent to improve the business case. Does also create business opportunities in new, but also in some existing customer segments, maybe customers where they are already doing the classical EPC. And then also play a new role in the aggregation value chain, becoming in fact technical aggregators of flexibility towards, for example, TSOs. EPC project facilitators, and me, myself, I'm Energy Invest, we are such an EPC project facilitator. We think we can use it also to convince end customers and investors of alternative revenue models, and there is a huge untapped potential. Also explore new advisory service that explore the flexibility potential, and we start having the first discussions, for example, here in Belgium with the federal government on using such flexibility, because they have thousands of buildings, and that's where it starts to get interesting also for them. And then of course we have to, and we see an opportunity to adapt some of our business models and tendering models to include APC. The DSOs, TSOs, of course, mainly in the case of what we call explicit demand response, where there is really a trigger coming from them to provide such flexibility, is to also unlock this untapped potential. Develop also new relations with ESCOs, as ESCOs, of course, are the primary managers of a lot of buildings for their customers. They may want to start doing business with ESCOs. And still, of course, the classical reasons for flexibility and demand response is improving electricity network resilience, also maybe delaying investments. This is an extract from one of the deliverables that we developed early on in the project. Again, not going into details, but it gives a little bit of status of the 4 countries that are part of the project, but also some of the other countries. And you see, of course, quite a lot of diversity. Spain is reasonably well developed in terms of ESCO and EPC, but there are some markets like Germany, for example, Austria, the UK, that are more developed. The same for Italy. If you look at the status of flexibility as a tool, particularly, we're talking really about buildings. There you see that Spain, for example, is not so developed. There is more development, for example, in Belgium, but also in Ireland, for example. And if we combine these 2 aspects, because that's really what is of interest, if we look at the potential for APC, how well is EPC developed, how well is flexibility already being used, or is there a potential being explored? You see that that from the 4 countries in the project, Italy and Belgium are a little bit ahead, and Spain is following closely, and then Portugal is probably a little bit less developed. But that was also the purpose, of course, of this project, is to work on not only on the business models and the technological solutions, but also on the market development, of course. Yeah. And we see that no country today is really fully green. Then I'm going to share some data from some previous market studies, some of them done by the Joint Research Center in Italy. Mainly the team of Paolo Bertolli, where we see this is a generic overview of the energy service market from 2019, so still quite recent, where you see that there are some countries that are really developing quicker, but sometimes that also means that they were lagging behind. And we see, for example, that Spain is part of a bigger group of countries in which the energy service market is growing. We have to also distinguish between the energy services market in general and then energy performance contracting, for example, in particular. Some are stagnating because there's less activity, or they have been maybe already developed very, very much, like, for example, Austria. And some are also declining, luckily not so many. If you look at the ESCO market itself, Europe on a European level, then you see that the European Union is not such a big market. It represents about $3 billion if you compare it to, for example, to China, which is a very big market, or the United States. What is interesting to see also is that in Europe, for example, the public sector is really pulling the energy service market development. Whereas you see in China, for example, it's more the private market. Same for other parts of Asia. And then some numbers from that study is the estimated turnover, so about 1.5 billion euros in 2015. This is for Italy, but there are similar numbers, for example, for Spain. If you look at it on a country basis, so this is an overview of all the countries. And we have here, for example, Spain, which is estimated in 2080 at about 1 to 1.5 billion. Again, this is the whole energy service market. On the other hand, some of these reports we also have to take with precaution. For example, if you look at the number of ESCOs, and that's probably a flaw in the study, that you see an increase, which is logical in the first years, but then it goes up to 1,000 ESCOs. I think that's really exaggerated. And then in 2080, only 70. So probably this number of 1,000 is wrong, but it should probably be situated in a couple of tens of euros in 2015, and then maybe a little bit more in 2008. It will be interesting to see how that has evolved over the last years. And again, also depends on, of course, the definition that you take on what is an ESCO. For example, in Germany, a lot of the energy service market is not about energy efficiency, about energy performance contracting as such, but it's more about energy supply, heat supply contracts. And these are a lot of smaller contracts and a lot of smaller ESCOs. Yeah, but that represents today about 90% of the German market. And so we could also expect in a country like Spain that there's probably a significant part of the market of energy services is about, for example, cold supply, maybe heat supply. And then another part is about energy efficiency, the traditional EPC contracts. We do have some EPC estimates from another study, also from the JRC from 2020. And there you see about 59 contracts estimated for a volume of 60 million. So you see that's already a more sizable part of the market. And roughly about 440 euros per square meter invested. Okay. So as I said, without being able to go into much detail, we did the stakeholder survey of roughly 20 stakeholders from 8 countries, either flex providers, mainly ESCOs, or flex requesters, so the DSOs, TSOs. And in the presentation, you will get more detail about it, but again, I cannot go into detail. This is an interesting table, I think, because it also gives an indication. If you then look at per building segment, where is the potential, again, in terms of EPC or in terms of flexibility. And then you see that the residential market, even though that's the case that we looked at in the Belgian pilot, has relatively low potential at the short term. Yeah. And we see more potential in the public and the commercial sector, because that's also where both the EPC market is developing more quickly, and that also flexibility potential that is being exploitable, let's say. The industrial market, for example, has a very high potential for flexibility, and that's where demand response today is thriving. But because of the difficulty to standardize solutions and the reluctancy to outsource, industrial customers do not use EPC very much. So it's really, in that sense, limited. But so most potential probably from the public and the commercial sector. So does this allow us to estimate the EPC EU market estimated anywhere between $1 and $3 billion, with a high potential, of course, for electrification in combination with solar PV and maybe even building integrated PV. But there is definitely a need to increase ambition levels. Another barrier is of course a limited availability of dynamic prices, but we expect this to be more commonly available in the next 5 years. Certainly with the increase also of pricing. And we do believe that based on the simulations, both static and dynamic, that an improve of the business case of APC versus the classical EPC of anywhere between 5 and 20% is probably realistic. And therefore, based also on the talks we had with ESCOs, we think it's not unlikely that maybe 20 to 30% of the EPC project will start including flexibility and thus become APC projects again in a period of the next 5 to 10 years. We're also finishing a survey now, a second survey of stakeholders, mainly ESCOs, project facilitators, and then EPC project aggregators, which are either one-stop shops or large building owners, on their application potential in different countries. And that hopefully will also give us more insight now, because we are, based on the experience of the project, trying to get them to ask more and more questions about how they can use APC, what usage they could see, for example, from a tool like ABIPEM and so on. And same thing for discussions if there's some topics I put on up here if needed. But that's it for me. Sorry for the quick pace, but not easy to get the 2 topics well explained in 15 minutes. Thank you.
Thank you, Levin. I think that you have provided a good introduction to the market, pointing out the main situation of the country, since, as you have said, it's not very common for all of us. We have the different countries have different particularities, I will say. And on the other hand, I think that the first insights from the Belgian pilot are impressive, and I think that will be very nice, because I think it will be easier to replicate in other buildings with these first results. So now we will move just for the end of the session. I will want to share my screen. I would like just to say 2 things. Sorry. As we have said, this project will finish next May, but up to that point, we are continuing developing different tasks. And as Levin has said, we have prepared a short questionnaire just to collect the feeling of the different stakeholders in the implementation of the AmBIENCE platform as a tool to offer active energy performance contracting services. So I have put in the chat the link to the survey. So if you feel interested enough to provide us some inputs, it will be really interesting for us, because we have to define the next steps to put this solution in the market. So that will be really interesting for us, because we will know how it's your impressions and which barriers you find and the drivers of this business. And on the other hand, we have defined also the final event that will be in Brussels, but since it will be also online, I will invite you all to attend and to register in this event, since it will be on the 12th of May. It will be just 2 sessions in the morning. The first one will be really focused on more the concept of the active energy performance contracting and AmBIENCE, while the second session of the morning will be more focused on experience, showing the best practices and the insights coming from the 2 pilots, because although we have been talking about the Belgium pilot, we have another one in Portugal. So in that case, we will be showing the the lessons learned from both pilots. And in addition, we will also bring some lessons learned from other projects. So in the AmBIENCE project website, you will find the link to this event, and you are all invited to attend. And I think it will be a good opportunity to learn a little bit more about the topics that we have been talking about. So that said, I think that is time for questions. I think that we have 10 minutes for questions, are discussing a little bit about the active managed building energy with energy performance contracting, but also not only focus on AmBIENCE, but also we can talk, or questions can be raised about the 2 other projects that have been